Now, let's take a look at using properties of logarithms to eventually help us evaluate logarithms. So before we get to solving for logarithms, we want to make sure we know some basic properties of logarithms. So here we're going to look at 4 basic properties of logarithms. The first one here we have log base b of 1 is equal to 0. Well, let's see, why is that true? Well, if we write that into the equivalent exponential form, then we have b raised to the 0 is equal to 1. Well, we know anything that's raised to the 0 power is indeed 1. So this is why we know that first property there makes sense. Okay? How about this second property? Log base b of b is equal to 1. Well, again, if we write that in the equivalent exponential form, b raised to the first power is equal to b. Well, of course, anything raised to the first power is just itself. So b raised to the first power, which is b. So b is indeed b. So this property makes sense as well. All right. So with the first two properties, we want to remind ourselves, anytime we have some log with base b, if we have a 1 here, it's always going to be equal to 0. With the second property, anytime your base is the exact value as your function here, if these two numbers are the same, it's always going to be equal to 1. Okay, so we have to remember that about these first two properties. Now, let's take a look at the next two properties. So if I have log base b of b to the x equal x, let's see, why does this property make sense? So again, if I write this in the equivalent form, take my base b, raise it equal to the x, and see, well, do I get it to equal to what I have there next to my log? So yes, indeed, b raised to the x is indeed equal to x. So we know that that third property makes sense as well. Okay, so this is how we are checking that those properties are true. Okay. All right, now finally, let's take a look at this property number 4. Well, I have base b, all right, raised to this exponent of log base b of x is equal to x. Okay, let's see why this is true. Well, first, if you remember, before we had this log base b of x, if you remember, we had that equal to something. So we're going to set that equal to y. And so if you remember, we can write this in the equivalent form, the equivalent exponential form, as b to the y equal x. Well, let's see what happens if we just simply replace this log base b of x with y. Then we would just simply have b raised to the y is equal to x. And we know this is the equivalent form of log base b of x is equal to y. So we're going to see if we can use these basic properties of log to help us to eventually evaluate different logarithmic expressions. So let's look at these examples. We want to see if we can use those basic properties of logarithms to help us evaluate each of these logarithms. So we want to solve for each of these expressions. So let's take a look at the first one. We have log base 15 of 15. Remember, one of those rules said if your base is exactly the same as your value here, well, that's just simply going to be equal to 1. So no matter what those two values are, if they're the same, this log is equal to 1. Now let's take a look at the next example. We have 8, base 8 is raised to log base 8 of 2. Well, remember, we said that we would set this equal to some exponent, some variable. Remember, we would change it to y. So we would have 8 to the y is equal to some number. Well, remember that rule. If that base b was exactly the same as this base b, well, this entire expression would just be equal to this value that's next to the log. But let's just remind ourselves what that property was. We have some base b raised to log base b of x. Well, that's just going to be equal to x. Okay, so if our base b, those values are the same, whatever we have next to our log here, that function there is just going to simply be equal to x. So therefore, in our example, our base is 8. All right, base 8 raised to this log base 8 of 2. So therefore, this must be equal to 2. So no matter what that base is, as long as it's the same there for both positions, whatever we have here, that's what this expression will always be equal to. And now let's take a look at the final example. We have log base 4 of 4 raised to the third power. So let's see if we can remind ourselves what rule this was, or which property we have for this one. So if we remember, if we have log base b of b to the x, then whatever we have there for that exponent, that's what this log is going to be, as long as our base b is the same as this value of this base b. So you can see here we have that base of 4, and then we have this exponential form, base b raised to the third power. So since those two values are the same, we have the same base there. So therefore, this log expression must be equal to 3. And so now we know how to use those basic properties, those basic rules there, to help us evaluate logarithmic expressions. Now, the next property we want to look at is the one-to-one property. So let's see what we mean by that. So let's suppose we have log base b of m is equal to log base b of n. Well, anytime we have the same base on both sides of the equation, we have one log each on each side of the equation, and they have the same base, then the one-to-one property just simply means that whatever the function we have here on either sides of the equation, they must equal each other. They must be the same. So the one-to-one property is just saying that if I have log base b, the same base on both sides, then whatever my function is here, they must be equal. All right, so it's technically look like we are dropping out the logs, all right, and just keeping the functions equivalent to each other. So if we take a look at this example, we want to see if we can solve for this logarithmic equation. So we have log base 3 of the function 2x plus 5 is equal to log base 3 of 3x. Well, we can see that on both end sides of the equation, we have one log each on both sides, and they both have the same base 3. Well, therefore, according to this one-to-one property, we can say that this function 2x plus 5 must be equal to this function 3x. So we're just simply going to set those two functions equal to each other and see if we can solve for x. So now we just treat this like a regular algebra problem. We want to get like terms on the same side, so let's get the variables on the same side, and then we'll get the constants over to the other side. So therefore, we just subtract this 3x over here with this 2x, so 2x minus 3x, and then we subtract this 5 over to the other side, so we have all of this is equal to negative 5. So now let's combine like terms. So therefore, we get negative x is equal to negative 5, and of course, we want to get this to be a positive x, so we can divide both sides by negative 1. So therefore, x is equal to 5. So we have just used that one-to-one property to solve for this logarithmic equation. We can always check ourselves. We can plug 5 back in to see if we actually do get the same expression on both sides of the equation. So just replacing every x we see with a 5, and we do get it to check out. 15 does indeed equal 15. So therefore, the value of x is positive 5. So that's how we can apply the one-to-one property only if the base is the same for both sides, and we have one log each on the left and the right hand side of the equation.